Imagine the infinite expanse of the cosmos, where stars flicker like distant campfires in an endless night. Somewhere among the countless galaxies, a profound mystery lurks in the shadows, a vast emptiness that could redefine everything we thought we knew about the universe. What if our own Milky Way galaxy isn't just another speck in a uniform sea of stars, but instead drifts within a colossal bubble of nothingness, a cosmic void stretching billions of light years across? What if this emptiness isn't just a quirk of space, but the key to unlocking one of the greatest puzzles in modern astronomy, the Hubble tension? This isn't science fiction, it's a hypothesis grounded in cutting-edge observations that's captivating scientists worldwide. As we embark on this journey through the stars, prepare to question your place in the grand scheme of things. If the idea of our galaxy floating in a giant void sparks your curiosity, stick around, because what follows might just blow your mind, and if it does, drop a like to show your support for exploring these cosmic wonders. Let's start at the beginning, with the very fabric of the universe itself. Picture the Big Bang not as a singular explosion, but as the birth of everything. Space, time, matter, all expanding outward like a balloon inflating from within. This expansion isn't static, it's ongoing, carrying galaxies away from each other at speeds that boggle the mind. Enter Edwin Hubble, the astronomer who, in the 1920s, revolutionized our understanding by discovering that distant galaxies are receding from us, and the farther they are, the faster they flee. This relationship is encapsulated in Hubble's law. Velocity equals the Hubble constant times distance. The Hubble constant, often denoted as h0, is the heartbeat of cosmic expansion, telling us how fast the universe is stretching right now. To grasp its importance, consider this. H0 isn't just a number, it's a window into the universe's past, present, and future. It helps us calculate the age of the cosmos, predict its ultimate fate, and even quantify the mysterious dark energy that's accelerating the expansion, measured in kilometers per second per megaparsec, KMS/MPC, where a megaparsec is about 3.26 million light years. H0 bridges the local universe we can observe directly with the ancient echoes of the Big Bang. But here's where the drama unfolds. Scientists can't agree on its exact value. This disagreement, known as the Hubble tension, has evolved from a minor quibble into what many call the most exhilarating crisis in cosmology. It's like two teams of master chefs arguing over the perfect recipe, only to find their dishes taste entirely different despite using the same ingredients. Diving deeper into the tension requires understanding the two primary ways we measure H0. On one side, we have the early universe method, rooted in the cosmic microwave background, CMB, the faint afterglow of the Big Bang that permeates all of space. This radiation, captured exquisitely by satellites like Planck and more recently bolstered by ground-based experiments like the Dark Energy Spectroscopic Instrument, DESI, paints a picture of the universe when it was just 380,000 years old. By analyzing tiny temperature fluctuations in the CMB and patterns like baryon acoustic oscillations, BAO, ancient sound waves frozen into the distribution of matter, cosmologists infer H0 with remarkable precision. As of October 2nd, 2025, the latest consensus from these methods, incorporating DESI's 2025 data release, pegs H0 at approximately 68.5 kilometers per second per megaparsec, with an uncertainty of about 0.8 kilometers per second per megaparsec. This value aligns seamlessly with the standard model of cosmology, lambda cold dark matter, lambda CDM, suggesting a universe that's 13.8 billion years old and dominated by dark matter and dark energy. Contrast this with the late universe or local measurements, which rely on observing nearby cosmic phenomena. Here, astronomers use the cosmic distance ladder, starting with parallax measurements of nearby stars, scaling up to Cepheid variable stars, whose brightness pulsates predictably, and topping it off with Type 1a supernovae, those brilliant stellar explosions that serve as standard candles across vast distances. The SH0ES collaboration, led by Nobel laureate Adam Rees, has refined this approach using data from the Hubble Space Telescope and, more recently, the James Webb Space Telescope, JWST. Their latest analysis, updated in early 2025 with JWST's infrared precision, yields an H0 of about 73.0 kilometers per second per megaparsec, with an an error bar of roughly 1.0 kilometers per second per megaparsec. That's a difference of around 4.5 kilometers per second per megaparsec, or about 7%, from the early universe value. In everyday terms, 7% might seem trivial, like overestimating a marathon by a mile, but in cosmology, where precisions reach 5 sigma, a 1 in 3.5 million chance of error, this gap is monumental. It's as if the universe is whispering two conflicting stories, one of a steady, predictable expansion from its infancy, and another of a hurried rush in the here and now. The emotional weight of this tension can't be overstated. For astronomers, it's a thrill mixed with frustration, a puzzle that keeps them up at night, pondering if our fundamental understanding of physics is flawed. Imagine dedicating your life to mapping the stars, only to find the map doesn't match the territory. This discrepancy has persisted despite decades of scrutiny, intensifying as instruments like JWST have sharpened our view. In 2023 and 2024, collaborative efforts between Hubble and JWST ruled out many systematic errors, such as starlight blending or calibration glitches in Cepheid observations. JWST's crisp infrared images confirmed Hubble's local measurements, eliminating doubts about observational artifacts. As Rees himself put it in a 2025 interview, with errors negated, we're left with the exciting possibility that we've misunderstood the universe. This sentiment echoes through the scientific community, fueling debates at conferences and inspiring young researchers to dream big. If this tension resonates with you, share your thoughts in the comments. What do you think is causing it? Your ideas might spark the next breakthrough. But why does this matter to us mere mortals? Beyond the intellectual thrill, resolving the Hubble tension could reveal hidden forces shaping reality. If the local value is correct, the universe might be younger than we thought, altering timelines for galaxy formation and even the emergence of life. Conversely, if the early universe holds sway, we might need to rethink dark energy's role. Scientists have proposed myriad explanations, from exotic new particles to modifications of gravity itself. Some invoke early dark energy, a fleeting force in the universe's youth that sped things up temporarily. Others suggest undiscovered neutrinos or even flaws in general relativity. These ideas, while innovative, often introduce complexities that spawn new problems, like conflicting with other observations. It's like patching a leaky boat only to spring another hole. Yet, amid this theoretical whirlwind, a simpler, more elegant solution has gained traction. What if the issue isn't new physics, but our vantage point? What if we're living in a special place, a vast cosmic void that skews our perspective? Transitioning to this hypothesis feels like shifting from a stormy sea to a calm harbor. Cosmic voids are the universe's empty quarters, immense regions where galaxies are scarce, gas is thin, and dark matter is sparse. If the cosmos is a grand web of filaments and clusters, voids are the gaping holes in that tapestry, like silent oceans separating bustling archipelagos. They form naturally through gravity's relentless pull. Over eons, matter clumps into dense structures, draining the spaces between them. The largest known voids, like the Bode's void, span hundreds of millions of light years, but they're not absolute vacuums, just underdense by 20 to 50% compared to the cosmic average. Visualizing one evokes a sense of awe and isolation. Imagine sailing through space where stars are few and far between, the darkness pressing in with an almost tangible weight. It's humbling to think such emptiness dominates the universe, comprising up to 80% of its volume. Our local neighborhood hints at this structure. Astronomers have long noted the local void, a smaller underdense region adjacent to the Milky Way, identified in the 1980s by R. Brent Tully and J. Richard Fisher, stretching 30 to 150 million light years. It's like a modest backyard compared to the grand estate we're now considering. But zoom out further, and evidence mounts for something far larger. The Keenan-Barger-Cowie void, named after the astronomers who first reported it in 2013. Using near-infrared galaxy surveys, Ryan Keenan, Amy Barger, and Lennox Cowie found that within about 300 megaparsecs, roughly 1 billion light years, galaxy density is 20% lower than average, gradually increasing outward until normalizing at twice our local density beyond that radius. This makes the KBC Void one of the largest structures ever proposed, with a diameter of about 2 billion light years, a bubble so immense it could swallow thousands of galaxy clusters. Subsequent studies have bolstered this picture. In 2014, researchers like Douglas Whitbourne and Tom Shanks used redshift surveys and peculiar velocities, galaxies' motions beyond pure expansion, to confirm a significant local underdensity. By 2017, analyses of standard candles like supernovae hinted at inhomogeneities. As of 2025, the evidence is even stronger, with galaxy number counts from surveys like the Sloan Digital Sky Survey and DESI reinforcing the void's existence, while not breaking the cosmological principle that the universe is homogeneous on the largest scales. The KBC Void pushes its limits, representing a rare fluctuation possible within lambda CDM, though improbable, about a 1 in a million chance. Living near its center challenges the Copernican principle, our assumption of no special place, yet it adds a poetic twist. Perhaps we're not central, just uniquely positioned in emptiness. Now, how does this void resolve the Hubble tension? The magic lies in gravity and perception. In an underdense region, gravity's grip is weaker, creating a subtle outward pull toward the denser walls. Galaxies inside, including ours, experience this as a gravitational outflow, like leaves drifting downstream in a gentle current. From our viewpoint, distant galaxies beyond the void appear to recede faster because their light climbs out of our gravitational well, adding extra redshift. This inflates the local H0 by about 5 to 8%, turning the global 68.5 kilometers per second per megaparsec into an apparent 73.0 kilometers per second per megaparsec, precisely matching the tension. No new physics required, just general relativity in an inhomogeneous cosmos. To illustrate, recall the raisin bread analogy. As the dough expands, raisin's galaxies move apart uniformly. But if our raisin sits in a bubbly pocket of less dough, nearby raisins sparse out faster, mimicking accelerated expansion. Or think of it as viewing the world from a valley. Distant mountains seem farther due to the terrain. Calculations from 2020 by Indranil Banik and colleagues modeled a 20% underdense void of 300 megaparsec radius, showing it boosts H0 by the needed amount. This isn't speculation, it's quantifiable, with the void's effects decaying at higher redshifts, aligning with observations where the tension fades. The crowning evidence arrived in 2025, courtesy of Indranil Banik from the University of Portsmouth and collaborator Vasilios Kalantzis. Presenting at the National Astronomy Meeting NAM in Durham, they analyzed 20 years of BAO data, those fossilized sound waves serving as cosmic rulers. Compiling 42 measurements from surveys including DESI, they tested two models, the standard void-free lambda CDM tuned to Planck CMB data, and a void-inclusive one. The results? The void model fit the data dramatically better, reducing tensions from 3.3 sigma to 1.2 sigma, and proving about 100 million times more likely. As Banik explained, a local void slightly distorts the BAO angular scale and redshift because induced velocities and gravitational effects add to the cosmic expansion. This predictive success, hypothesized before the data, lends immense credibility, turning skeptics into believers. Yet this revelation stirs deep emotions, awe at the universe's scale, humility in our isolation, and excitement for what it means. If true, it preserves our standard model while reminding us that assumptions of uniformity can blind us. Philosophically, it echoes ancient debates about humanity's place, neither central nor average, but in a void that shapes our view. It prompts questions. How else does our locale bias observations? Might dark energy's discovery in 1998 have differed in a denser spot? The void hypothesis fosters universal appeal, inviting everyone to ponder our cosmic home. Of course, debates rage on. Critics argue the void is too large for lambda CDM, potentially requiring modified gravity like MOND. Reanalyses of supernova data in 2025 claim biases weaken the evidence, and some JWST measurements, like Wendy Friedman's 70.4 kilometers per second per megaparsec, suggest the tension is easing without a void. But proponents counter that multiple probes, galaxy counts, velocities, BAO, converge on the underdensity. The discourse is vibrant, a testament to science's self-correcting nature. Looking ahead, missions like the European Space Agency's Euclid, now fully operational since its 2023 launch and releasing data streams in 2025, will map large-scale structures with unprecedented detail. NASA's Nancy Grace Roman Space Telescope, slated for launch in 2027, promises even finer resolution. These will probe the void's boundaries, measure outflows, and test predictions. Whether the void holds or crumbles, the outcome thrills. Either a grand illusion or new physics awaits. In closing, this cosmic enigma reminds us of the universe's boundless mysteries, a tapestry woven from the threads of the unknown that continues to pull us deeper into its folds. From the Hubble tension's stubborn gap, a rift in our cosmic map that challenges our deepest assumptions, to the void's embracing emptiness, a silent guardian that might hold the key to harmony, it's a story of discovery laced with doubt and shimmering with wonder. We've journeyed through the heart of expansion, peeked into the shadows of voids, and felt the gravitational whispers that could rewrite our place in the stars. If this narrative has ignited your imagination, fueling that spark of curiosity about our vast, enigmatic home, hit that like button to signal your wonder and comment below with your take. Do you buy the void idea, or do you sense something even wilder at play? Share this exploration with friends and fellow stargazers to spread the awe far and wide, because in unraveling these puzzles, we're not just learning about the cosmos, we're reconnecting with the infinite curiosity that makes us human. Together, let's keep gazing upward, hearts open and minds alight, unraveling the stars one breathtaking puzzle at a time.